Thanks for coming back, Jeff.
I haven't even said anything about getting claps. Thank you. So I was sort of gifted this hour to talk about whatever I want. And so I decided I would spend a little bit of time talking about cutting edge topics, which really just translates to my research. But then I'll spend a little bit of time at the end of the half hour, I suppose, doing a little bit of a career panel. I hope that's okay. I'm springing this on people. We'll turn the recording off, and then hopefully we can have sort of an honest discussion about, what it's been like for us in the field, what maybe questions you have that you don't feel comfortable asking other people, and hopefully, we can all, learn something maybe. So we'll start with some things I've been thinking about, and that's related to how you can understand LIGO sources using other data sets. And there's reasons I think this is really valuable. One is LIGO actually doesn't provide that much information, right? For any individual observation, you have two masses, which are relatively poorly constrained, and a spin, which is relatively poorly constrained. So, and some distance, whatever. There's other things. But the point is that it's really useful to be able to combine information from LIGO with other things that we see astrophysically in the universe. And that's really what I'm going to try to focus on here. A couple ideas about ways you can do that. And so there's actually a lot. So there's a lot, particularly, I actually think that you all are in kind of a magical era in our field, because we have these massive data sets, and there's a lot of funding to produce these massive data sets, and there's a lot of potential as a result. And that includes both space-based telescopes. LISA is coming online, but that's not for another 15 years. So in the intervening 15 years, there's so much that's going to happen in astrophysics and astronomy. I'm just throwing up a few examples. TESS is one. It's a NASA mission. It looks at light curves all across the sky. Gaia is another. It gets, it's an ESA mission, and it looks at, 1.5 billion stars. And all of these things can help us to learn. On the ground, we have radio telescopes. SKA is coming online. There's many other radio telescopes coming online, CHIME. And then there's plenty of observational resources that are coming online as well. LSST, for instance, is coming online very soon, in like 2 years, something like that. So we're going to have all these astrophysical transients, and these are enormous data sets. They're actually going to dwarf what LIGO can see. It's just LIGO is a whole new era. It's a whole new vision for how we can see things. So all I'm trying to say is that there's all these different ways to complement the data sets from LIGO with other data sets. And it's really useful to think about how maybe in your research, you could do that too. So I'm going to go back to how you form double neutron stars. Again, double neutron stars are things I love, I care about. The same thing works for double black holes. So one thing to really emphasize this is the generic pathway to form two neutron stars that end up merging and forming a LIGO source. Every stage is 2 stars in every step. And what's really cool is you can go through these and you can actually identify observational counterparts in our Milky Way that go along these pathways. Wolf Rayet stars, supernova, there's a few where we don't actually see these types of systems just yet. But high mass X-ray binaries, common envelopes, maybe we see luminous red novae, that's another topic. And so I'm throwing out a series here. And the important thing is, if you look at this, we really do have a picture of every stage, except for a couple, of how you form double neutron stars, right? And the same thing more or less goes for double black holes, is that you can see images at every stage. And if you can put them together in a coherent enough way, you can actually sort of solve the problem from all these different perspectives. So I'm going to focus on
Jeff?
Yes, please ask. Please, by the way, interrupt me with questions if you can.
So maybe I missed it, but this check mark and cross means that they have been observed optically, or
That's the idea, is that the check mark means they've been observed
optically or something.
Let's say with electromagnetic radiation. In fact, I actually have the merger down here, so also with LIGO. But yeah, the point is that we have an observational, it's not just on paper in theory, we actually have a counterpart that we observed. Okay. The X's are places where either we haven't or we don't know if we have. There are
Hey, Jeff.
yeah, what's up? How you doing?
Just quick.
What,
Oh, thanks, bud.
There we go.
Okay.
Sorry.
what about the question mark?
Yeah, question mark's a good one. Thanks, Miguel. So this was one where I think other people have said this too, but we sort of theorized this in a paper a couple of years ago where we said it's possible that ultra luminous X-ray binaries are actually this particular phase of it's a thermal relaxation phase after a common envelope where you have mass transfer, and we said maybe that's because. So the point is, we see ultra luminous X-ray binaries. You know, they could just be normal X-ray binaries in some weird, highly accreting state, or they could actually, some fraction of them or all of them could be in this phase of special case BB Roche lower flow.
I was going to say observation might be almost exactly the same. Except
Yeah.
that I would expect to see a lot less of these special ones than the standard type.
And we do. The hard part is that they're really bright. You see
Yeah.
them farther away, and so your statistics are sort of screwed there. And plus, with X-rays, you have confusion, so two sources can come together and look brighter than anyway. It's X-ray binaries are a tough one.
I have a question.
Yeah, please.
That particular question mark, like
Yeah.
when it is separated into it, what happens to will the pulsar stop pulsing signals or can you tell more about it? What happens to it?
Yeah, so essentially, when you have a pulsar that accretes mass, it quenches the pulsing mechanism. So neutron stars that are pulsars and they're accreting, they will stop becoming pulsars. That's typically how that happens. And we actually know this, we've seen this to be true. There are these like missing link pulsars. They're essentially systems that go between being a pulsar and a low mass X-ray binary. And they go back and forth. And there's a few that we've seen that do this. So essentially, we have a pretty good idea. If you put enough ions in the atmosphere, it'll like quench the mechanism. And that's I don't want to say it's super well understood, but I think there's, you know, the basic process is pretty well understood there. So it stops becoming a pulsar, but it's still a neutron star. It's still doing its thing. And as soon as accretion stops, then it will become a pulsar again.
So what are the expected observation signatures, like sudden spin down or something?
Sudden spin down. Why?
Yeah, like stop.
So essentially, if you have a pulsar that's accreting, it'll produce X-rays. Because the material comes on, it heats up, thermalizes, and you know you get close enough to the inner edge of the accretion disk that it produces X-rays. So we think essentially how bright the X-rays are depends upon how much mass you're cramming in, and we think in this particular phase you can actually dump quite a bit of mass onto a neutron star at a very high rate. Okay, cool. So there are other examples. Ultra-strip supernova. We have seen ultra-strip supernova. We don't know if we've seen one that has a companion that is a neutron star, for instance. So we haven't seen that, but we have seen ultra-strip supernova. So there are other analogs here I'm sort of putting under the rug. But the fact is, we've done a pretty good job. Alejandro?
So, comment on the first X on the left column.
This one.
Yes, what do you mean with the system? Will be X-ray binaries qualified there, or just because they're not an X-ray binary?
It's valid, yeah. These, I would say, I'm throwing BE X-ray binaries into this stage.
Yeah.
For many systems, you jump right from here to here. But for some systems, there may be these detached examples. And that's such a great segue. Thank you. I should have thrown that question because I'm going to talk about exactly those systems. Okay. So we have a particular class of systems that I'm interested in where you essentially can't see them. Why do I mean that? I mean that all the normal ways you'd look for these types of systems through X-rays, for instance, through accretion physics, you don't see. And the idea is that the neutron star or black hole is far enough away from its companion star that you just don't get enough X-rays to observe. You look at your telescope and it's below whatever upper limits you can produce. Okay, so it's faint. That's the point. It's very faint. So how do you find these? Well, in the past, and I mean the recent past, although the method is over 50 years old, in the recent past, the way you do it is with the radial velocity method. Okay, this is basic astrophysics you can get from a textbook, but I'm putting some math up here in case you're curious. Essentially, one star gravitationally swings the other star around it. That swing causes a Doppler shifting. So if you take radial velocities of it, you see a progressive shift in the radial velocity. whatever lines you see, your H alpha line goes up and down. Okay, for instance, it shifts wavelengths, and so that's from Doppler shifting from, and you can actually backtrack what the orbit looks like. If you had eccentricity, it's a really minor, well, you can observe it, it's all figure outable. And you have this one thing which you don't understand, which is the inclination angle, which is very frustrating, but you can do this. You essentially can see these oscillations and you can determine that the system is in a binary. You can place constraints in the mass of the companion, all these things. So if you don't know what the inclination angle is and you see some oscillation, you say, all right, I don't know what the companion is, but I know at worst, it's edge on. And if it's edge on, you are putting a minimum mass in the companion. So let's imagine I have a 2 solar mass star. I see its 2 solar masses oscillating, and I come up with a minimum companion mass. I go through this mechanism. I figure out what M2 is. My minimum companion mass is 3 solar masses. Well, that's quite strange because I have a 2 solar mass star. I see its 2 solar masses. My spectrum tells me it's 2 solar masses, but I know there's something that's 3 solar masses that I'm not seeing that's there. A 3 solar mass star typically is brighter than a 2 solar mass star. So if you don't see your 3 solar mass star, it means it's quite faint. It's probably a black hole. Does that logic make sense? That's the idea. It could be a dwarf. There's, yeah. People tend to put that in the footnotes, possibly. Yeah, could be a dwarf. Yeah, now you're asking the good questions. So,
Because I mean,
yeah.
it could be strict stars, but then strict stars are typically lighter.
Yeah.
Again, than
Yeah.
the main sequence counterparts.
All right, so I'll
Sorry.
ask me that question in like 2 minutes. Okay, then we'll get to that. Okay, so here's 2 examples of these types of binaries. On the left, we have this particular system. Again, look at the dates. This is all very recent stuff. These are the first systems that have been discovered like this. Okay, this is from 2019. It's a science paper, and the top is showing photometric variations, and the bottom is showing radial velocity variations. Okay, so you see that there's oscillations, the photometric and radial velocity oscillations are in the same period. There's good reasons to think it's a binary. And you see the magnitude of this variation. It's actually quite large. It's 80 kilometers a second peak to peak over an orbital period of like 80 days. You can come up with a minimum mass for that thing, assuming you understand what the mass of this star is. We'll get back to that in a second. On the right side, this is actually really cool because people have done this, in particular this group. Geysers, actually, it's one of the European groups. I'm not exactly sure where they're from, but I think they use VLT for this. And you need the angular resolution and you need very bright telescopes or big telescopes to see these faint objects. But when you look at this is in a globular cluster. It's an NGC 32. It's a globular cluster, whatever. And you take spectra of it and you see this really cool stuff, right? This huge variation, peak to peak, it's 125 kilometers a second. Massive. And what's really cool is it's eccentric. Now you look at this and both of these groups have gone through this analysis and they say, if you look at it, it has to be something very dark and very massive, which they both claim it's a black hole, which is a reasonable claim actually. But it's really cool. This is in a globular cluster. I mean, this is potentially a dynamically formed binary, has all the signatures. It's a black hole with something else. It's high eccentricity and is exactly where people would think they should be in globular clusters. So that's actually really cool. And this is, I think, not the only one this group has found, but essentially, you can do this kind of analysis. This one's a little bit trickier. And the question was asked, how do I know it's not whatever? The reason is that this is a giant star and giant stars are very bright. Potentially you can hide non-giant stars in there. I'm going to put that under the rug because, well, I'm going to put it under the rug. Question in the back.
I have another question about stars. Aren't like the white dwarf star binaries the most intense gravitational wave giving signal kind of star? I mean, at this there's a huge deal about checking the background of the white dwarf binaries, but not other stars. Like there's a particular reason why the white dwarfs are like the most intense, or
yeah. So the question is about white dwarf binaries and their gravitational wave signals. So there's a few answers to that. One is they're the most numerous objects, white dwarf binaries, which means on average, they're going to be closest to us. So for things like LISA, where you see them at the right frequency, they will be potentially the strongest signals. We've already gone earlier in the week, we've said, we know some that will give off gravitational waves, and LISA will be able to detect it in like 5 minutes of observation, something like that, right? So we know that certain systems do exist like that. I think, we get to a little bit of a semantic argument in terms of most intense, because then you have two supermassive black holes halfway across the universe, and we'll see it from everywhere, right?
Yeah, but I mean, what are like other star binaries taken in consideration?
So other binaries are. So the rates are just really, really not great. So for instance, if there was a double black hole at the right phase of its evolution in the Milky Way, we will see it with LISA.
Definitely.
The problem is the rates.
Yeah.
There won't be very many of them. So we could get lucky and see one. Chances are not. So we looked into this for double neutron stars, and the rates are high enough, we expect aborted dozens. And that I think is a very interesting LISA signal, and something that I care very much about. And we potentially can see them in Andromeda as well. Maybe we'll see a couple in
So
Andromeda.
it's only because of the high density of white
The high density is the critical piece there. Yeah. One more question in the back.
Yeah, I want to be pedantic on what you said, and focus on the word potentially that you used, because if we go back in time at the LIGO, we also thought that the greatest signal would come from neutral stars, and then we were right. So is this potentially, as you said it, unlikely?
So it's a good, so the question is related to, in the past, we've been incorrect about our gravitational wave predictions in terms of types of signals. Could we also be incorrect about LISA?
Yeah,
right.
What's the margin of confidence?
Yeah, the answer is obviously. I mean, I'm not as pessimistic though, because I think now we actually do have observational limits on the rates of these systems.
Okay.
So we have pretty good estimates from multiple methods on the rates of double white dwarfs that exist in our Milky Way. And we have LIGO estimates on the rates of double neutron stars and double black holes. That wasn't the case before. So I'm a little more optimistic. There's specific reasons why we screwed up our models for black holes. In particular, we didn't take into account low metallicity stars. But we can get into that. Yeah. Martin, was there?
Actually, I was actually going to ask whether you can explain what went wrong.
Yeah. So I can go into it a little bit further. Essentially, we thought that all the double black holes, anything that was low metallicity would be too far away, and they'd be too faint for us to see. So people were focusing on high metallicity, Milky Way metallicity type black holes. And when you put those sort of two errors, and when you put them together, you realize that not only do low metallicity black holes produce more massive black holes, but essentially because they produce more massive, you can see them more distant. And that was the problem with our models in the past. Anyway.
Can I ask another question?
Yeah.
I don't know if you mentioned this, but are there any constraints or ideas on the rates of the double neutron stars that could form dynamically? Like you would say,
There are constraints. Yeah, I will. Yeah, no, please keep me honest. So the question was, are there constraints on the rate of dynamically formed double neutron stars? The answer is yes. The constraints are largely theoretical from models of globular clusters. And if you trust those models, and I see no reason not to, they predict that there will be a small minority of double neutron stars will be formed dynamically. Some, but the vast minority will. Okay, another one in the back.
Just another small question.
Okay.
What about neutron star white dwarf binaries?
So it's a good question. Those exist.
What's the question?
Yeah. Thanks, bud. So the question was about neutron star white dwarf binaries. And I think you just said, like, what about them? Yeah. They exist. I think it's a whole area of research. I think they haven't been looked at enough. I think it's definitely something that needs to be looked at more. Potentially they're LISA sources. They can, in principle, form dynamically in clusters. It's unlikely just based on details of models. I can explain why, but it's not important. But essentially, they should exist. They should be relatively common. We know of some that do exist. We know of a handful that we've detected. Essentially, you see the pulsar and you see the companion. The companion's a white dwarf. We know of actually many of those. Rates, I do not know what the rates are.
Okay.
Yeah, so I think that actually is something that somebody needs to look at, Lisa. Maybe they haven't, I just don't know about it. Okay. But here, I'm actually going to talk about something else. So moving on, I'm going to talk about Gaia. I'm going to skip this slide. And I'm going to say, all right, so we're going to look into the sky and we look at a star. Okay, star it exists. It's up there somewhere in the sky. And you look at it and you look at it for a long time, very, very carefully. And you say, aha, it's not moving. But that's wrong. Stars move. They move from two effects. First, from parallax. Okay, this is the idea the Earth goes around the sun. So every star, if you look at it carefully enough, makes a little loop in the sky. Okay, some little ellipse. And then the second effect is all stars are moving on the sky. And when you combine the two effects together, every star in the sky is making a little helix in the sky. Okay, cool. Does that make sense?
Is
All right.
the second effect proper motion?
Second effect is proper motion. Okay, so proper motion and parallax combined make these little helices. Every star is doing this. Okay. Now imagine if you observe this star and in fact, it looks like that. What's going on here? Well, maybe it's quite obvious. There's another star or planet around it that's moving, making it move. So you have this higher order effect on top of the motion that you see. And so this is called the astrometric method. Question in the back.
Are the planets like really that much affecting a moving star? Like
Well,
they would probably be another star or a planet, but the planets are
yeah.
like.
So the question is the effect this strong from even a planet? And the answer is it could be. It could be. I mean, you could take a very massive planet, something just short of a brown dwarf, and depends on how massive this star is. So if this is a brown dwarf, sure, a planet could whip it around quite a bit. It depends quite a bit. This is an example. I forget exactly what I used to make this simulation. I mean, this is a real simulation of a real observation, but I forget exactly what parameters I used. You can also estimate, by the way, you can estimate the orbital period. You know, this is 1 year, this loop, and you can say how many curly Qs. I don't know, it's like a month, right? So you can do all this sorts of things with this. In practice, there's a problem here, and that there's a degeneracy in the orbit. So for the exact same star you see, this is luminous star, you can actually come up with combinations that are identical for different masses, where this is a star you don't see. Depending on the mass of the two masses, you have, there's a degeneracy you can't break, is essentially what I'm trying to say. So we looked into this in a paper a couple years ago, and we actually calculated how well you could measure these types of systems. The hope is, of course, you can actually measure the mass of the star you see. And if you do that, you break the degeneracy. Okay. So the way you do this, of course, is with Gaia. Gaia is this telescope. It astrometrically measures the positions of all stars in the sky that it can see. It's over 1.5 billion stars. And it detects the proper motions, the parallaxes of all these stars. In practice, you can only get accurate measurements for the nearby ones, but the nearby ones is still over 1 million. It's over like 100 million stars. Like, several 100 million stars. You have very accurate orbits for it. Yeah.
How does Gaia keep track of the same star? Like, is it luminosity or?
So it has its own map. It has its own sky map of stars. It's just constantly scanning the sky, taking pictures every. It's a complicated scanning law, but it ends up that it takes multiple pictures. So over 5 years, it'll take something like on average 70 images of the same star in 5 years. And that's enough to find these oscillations, both proper motion, parallax, but also any oscillations on top of that.
Okay, so we say that, okay, star cannot move that fast or that slow, so we just figure out.
Yeah, essentially. So in practice, what you actually do is you fit one of these orbits with it. And people have gone a little bit deep into exactly how you fit these orbits. It ends up being quite linear. And so you fit this, and then you say there's a lot of astrometric noise on top of that fit, and that indicates the presence of something else which is causing it to wobble. Okay, there's a question in the back.
Yeah, what are the bands?
What are the bands of Gaia? Like photometric bands, you're saying? Yeah. So Gaia has 3. It has a white light filter, which it calls G. It's essentially everything, and it has a blue and a red filter. Those are the bands that Gaia is observing. Optical. It's all optical.
But it doesn't matter spectrum.
It has a narrow band spectrum that's focused. So the question is, it doesn't measure spectra. It does, but only near I think it's the calcium H and K line. I think it does. And it does that for radial velocities. So it gets radial velocities for everything that's brighter than, say, 14th magnitude as well. but it's quite narrow. So you get a couple iron lines out of that as well. All right, question.
Yeah, I think Gaia found a large number of these twin binaries, like equal mass binaries, right?
Mhm.
And I think someone made the explanation that this is because of binary accretion, that the mass ratio equalizes. But is that necessary, or is it likely that stars are born at the same mass?
Okay, so the question was that it was commented that Gaia has observed lots of twin binaries with similar masses, and then the explanation was, is that because accretion sort of pushes them to become sort of equal mass? Is that, am I following that right?
That explanation was used, but I'm not sure if it's necessary.
Okay, yeah. So yeah, I have a few thoughts on that. So first of all, Gaia has not yet released its catalog of binaries. It has catalogs of binaries that people have come up with where they are wide binaries. And that's something else I've looked into that I'm not going to talk about today. But essentially, these are wide binaries. And for those binaries, you can say, why are they more typically similar in mass than not? And at that point, you have to go pretty deep into star formation and how you create stars out of gas clouds. So to be quite honest, I don't know that much about it.
I thought they were only found at short periods.
Sorry, what was only found at short periods?
The twins,
The twins.
as far as I remember, at least speaking about massive stars.
Okay, if this is a specific paper, then I'm probably not going to know it, but we can discuss it. Yeah. For massive stars, when we do population synthesis, there are ideas that there are more binaries with similar masses at short periods. I think that probably is not from Gaia though.
No, yeah.
Is this El-Badri?
So the El-Badri paper, that one is about wide binaries.
Probably easier to detect the squiggles if it's equal mass.
All right, so let me keep pressing on before we run out of time. So essentially in this particular work, we used synthetic Gaia observations to calculate exactly how well Gaia will be able to measure these types of binaries, these astrometric binaries. This x-axis is orbital period in days, and the y-axis is a mass measurement precision. It's something like a precision on the combined masses. You can take it sort of, it's almost a measurement on the companion mass, and lower is better here. So lower is telling you that you can measure the mass to 1 part in 10 to the 3, for instance. So it's a 0.1% mass measurement. Now the different lines are telling you different distances. So if the binary that you only see one component of is at 10 parsecs, then you can measure it quite well at 100 parsecs and then a kiloparsec. Now this is for a 1.4 solar mass hidden objects. That's a neutron star, but you can play the same game for any different variety of hidden stars. And so you can play this for brown dwarfs all the way up to black holes. And depending upon how massive it is, you're sensitive to different distances, these types of binaries. Okay. So essentially the whole point is that we calculated exactly what this is. There's more astrophysics in here that I'm not going to discuss, but feel free to ask me questions on it. And then I'm going to go one more step further and say, what about even wider binaries? Okay. So I showed you in that first example, the curlicues on top of the curlicue. That was a binary with an orbital period of like a month. What happens if the binary period is longer than Gaia's lifetime? Let's say it's a 50 or 100-year orbital period. What happens? Well, it looks like this. So a normal star without a companion goes off, helix, okay? If you have this in a wide orbit, there's a little bit of an arc to that helix, okay? What you're measuring is an acceleration. And that acceleration could be due to any number of things, but I'm going to assume it's due to a star, some other star. So this is essentially the way you can identify whether a star is in an even wider orbit. And this is a paper that it's not even in the archive, but I've submitted it. But essentially you can actually, in principle, you can detect, this is a detectable signal. And so we did some calculations, which shows you what is the orbital acceleration as a function of true anomaly or eccentric anomaly in this case. And it varies based on your eccentricity of your orbit. Of course, if you have a highly eccentric orbit, then at some places it's going to look a lot straighter, and in some places it's going to look a lot more curved, so different accelerations. But it's easily, this is just Keplerian dynamics. Any one of you can work it out. And yeah,
Yeah, how degenerate this example signal is with distance? Because it changes the size of the parallax.
It actually probably won't have too much of an effect on the parallax. You can probably disentangle the parallax pretty well from the acceleration. So you probably have a pretty good sense of what the distance is. What you don't know is the relative inclination of the orbit, and that's a little bit tricky. That's true. So that's an effect. We looked into that a little bit. It ends up being not super important because, to be quite honest, you're not going to be able to determine that much about these binaries. So there will be degeneracy between the mass and the inclination for the companions, but it's a factor of a few, which is good enough. Alejandro.
Yeah, I wasn't aware of this work of yours. Is this how sure you are that this, or confident one can be that this is a wide orbit and that there's some degeneracy with other parameters of the binary? Like, I've never thought about this.
Essentially, what you're seeing is an acceleration in your orbit, and that has to be gravitational. I'm trying to think of other things that could be going on here, and I can't really think of one. You can have some acceleration if you have like a passing molecular cloud, but it has to be, yeah.
Like, you only know like they look quite similar, right? That
Yeah.
two structure. It's not like the wiggly one where you could really see that there was something not happening. So I'm trying to understand, and maybe we can talk about this later. Why would one, like, why would you know what the reference is? Like
Yeah.
what are the error bars
Yeah.
in that
Yeah.
blue curve? Are they within the width of the line?
So the error bars are quite complicated for Gaia, but the fact is that essentially you can measure that there's a little bit of an arc to your orbit. That's as simple as I can put it. You try to fit the orange curve with a straight line, and you're going to find there's a deviation. That's all. And so we actually quantified what that deviation looks like, the magnitude of it, and came up with estimates for what that's actually going to be. It turns out your measurement, your acceleration sensitivity is not so high. So there's a lot of ways to interpret this, but the best is if you look at the top axis, the acceleration, and this is showing you the same parameters as before. So essentially you can measure accelerations down to the y-axis is the same. So you can get accelerations of say 10 to the -2 and 10 to the -3 for binaries that are nearby, maybe even 10 to the -4 if it's really nearby. You can start to measure these accelerations. Yeah.
Yeah, how could you say if it's a bound wide binary or if it's just a flyby or something?
That's paper 3, which I'm in the middle of writing about. So yeah, we look into flybys as well. In practice, you're going to find that those are extremely rare. So in practice, what you'll find is that almost every single one will be a bound binary, just statistically. Yeah.
Is a triple signal at all interesting?
Yeah. So that's not a paper I even thought about, but yeah, triples would have a similar effect as well. So if you found binaries that are doing this, and certainly you will, if any of these happen, you can go back and you can say, all right, we see an accelerating signal, then let's look at one star. Is that star orbiting? Does that star have its own signature of binarity, photometric variations, radial velocity variations, whatever? And you will find samples of triples. Those exist out in the universe. We know they're there. We know of some triples that have long orbital periods of hundreds of years and shorter, we know they exist. This is a good way to find many more of them. Yeah, that's a really good idea. Cool. Okay. So anyway, we did some population synthesis, which makes some predictions. We should see dozens of these. That's like dozens plus or minus an order of magnitude, because we really don't have great statistics on how many of these should exist. And there's a second thing, which is even if you have these, you're only going to be able to find black holes in certain cases. I don't have a great way of explaining this just yet, but essentially you have even less information about these binaries, right? All you're seeing is a little bit of acceleration, and you don't know the inclination angle, you don't know the mass, etc. So only in certain cases will you be able to take these and then go back and say, aha, this is a black hole, which is really what we care about most. But it is possible in certain regions of parameter space. And that's what I mean when dozens. When I'm looking at dozens, I'm talking about black hole companions. Neutron stars are sort of the same as well, but neutron stars get kicks and whatever. So
Jeff, when you figure out like what is interesting, is it straightforward? You can tell someone use your telescope and see this. Is that also a big mess? Or what
yeah,
are your plans?
so essentially you'll come up with a whole set of these systems, and you'll say the companions of these systems are interesting. And then of those companions, yeah, people should go back and look at their telescopes, and then they should say, aha, we have interesting systems. Can you find that, wow, what that companion is? And they can't find something, then maybe it's a compact object. And if they can, maybe it's still interesting. But yeah, essentially we could tell people where to look to try to find faint companions, probably adaptive optics. Okay, cool. So last thing, we did some population synthesis. Gaia should observe combined, mostly the short period binaries, the astrometric binaries I first talked about. We expect something like thousands of these to come into play. There's many other people who have looked into this type of study. I think I'd argue we did the most careful job understanding Gaia's observations, but something like 1,000 of order 1,000 binaries we should get out of this. Now, where this is really exciting to me is that Gaia exists in the sky. This is not a planned mission. It's something that's there. The data for the next data release has already been taken, already been downloaded, and it exists. It's now just up to the Gaia team to interpret this data and come up with a data set. So this is not theoretical at all. This data exists in a hard drive somewhere, which is very exciting to me because the next data release is the first half of 2022. So this is imminent. This data set is imminent. And if you look at the specifics, you find that they're very big. Non-single stars is exactly what they say. So what that actually means in practice, and I've talked to people on the team, they will come up with a set of astrometric binaries, and they will come up with a set of these accelerating binaries that don't quite have a straight line, that will have some arc in there. And so it's sort of up to us, the rest of the field, to interpret that data set, mine that data set, and say what they're actually seeing. I can get in the back.
So just a data question. So does it mean that the post-processing of the data includes like tagging of potential binaries? So you don't have to do that yourself?
Yeah. So what the question is, what is Gaia actually going to produce? And essentially, so far, things that are obviously binaries, Gaia has actually taken out of the catalog. So if you were to download the catalog today, all of Gaia, there are objects that Gaia sees, that Gaia knows it sees, that it is kept out of the catalog because they don't essentially want to give you bad data. That they know the parallax measurement is bad because it has these astrometric motions inside it. So that's a data set which they will release, and they will say, this is a binary with these characteristics. Cool. Okay, so that's all I had. And actually,